Yes, so I guess there are two promising features in this constructor theory program, which are also shared by other efforts that are taking place currently in physics, which are the fact that the laws that we proposed were scale independent, or they had the ambition of being so. So scale independent means that they are intended to apply to physical systems irrespective of their size. This is important because, for example, there is to this day a controversy about whether, for instance, the laws of quantum theory, which is one of our best current theories of physics, would apply to all objects irrespective of their size. And of course, quantum theory is supposed to be universal in this sense, but some people question that. And so the fact that constructor theory was trying to address this problem of formulating laws in a way that are scale independent was one promising feature about it. And there is the other promising feature is that laws of constructor theory are intended to apply to physical systems irrespective of their the details of the particular dynamical laws or laws of motion that they obey. And so in this sense, they are particularly suitable to make predictions in those cases where we don't yet have a law of motion like, for example, Newton's laws for physical systems, but we can make general statements about what transformations are possible in those systems and what transformations are impossible. And in this sense, I think the laws of constructor theory are intended to generalize the spirit of the laws of thermodynamics, like conservation of energy or the second law, which exactly are supposed to apply to a large class of physical systems, irrespective of what dynamical laws they obey. So these two features have become important in the context of this new piece of work that brought together tools from quantum information and also tools from constructor theory, conceptual tools from that area, which pertains to making predictions about what happens when you have a quantum system interacting with gravity. The reason why this is an example of a hybrid system, the system where you have a gravitational field interacting with a quantum object, is that to this day we don't have a specific dynamical law that describes such a system. There are proposals, but we don't know yet which one is the right law, and therefore this principle-based type of approach proves helpful in this context. And there is a nice unifying way of looking at such systems that actually stem from quantum information. That is to say that all such systems can be regarded as objects that can store and be used to process information. So I guess when you consider a composite system of a quantum object, like a mass that can be put in quantum superpositions, and you treat that mass as a qubit, and then you wonder what happens when this qubit interacts with the gravitational field, and you regard that as at least as a bit, so it's an object that can contain classical units of information. Then you can start wondering, by using these information theoretic principles, what type of predictions you can make about the composite system, even though you don't know what is the exact law of motion that applies to this composite system. Okay. And this is a bit the logic of this work that I was mentioning. So the logic is that we consider two quantum objects which can each exist in two locations at the same time, so they can be put into these two states that are quantum superpositions of spatial locations. And this has an effect on the gravitational field. The idea is that if we leave these two objects by themselves to interact through gravity, and at some point later we find out that they are entangled, so they evolve to a different state, which has this particular quantum property, which we call quantum entanglement, which can be measured by performing measurements just on those two systems, then gravity must be responsible for this. And this tells us something fundamental about the nature of gravity. So if it can be used to establish entanglement between these two quantum objects, then it has to be quantum itself. So it has to be capable of existing in a superposition of different states. And the interesting thing is that in this case, you don't have to perform a measurement on the gravitational field directly, but you can probe its features, quantum features, just by using this indirect test of using these two masses as a probe. And I think this is the strength and the new element with respect to proposals that were made in the past. So it was, yes, because we came to this idea through a sequence of other papers that were trying to study what type of predictions you can make about these hybrid systems where you have a qubit and, something like a qubit and another system which you can assume safely behaves like a bit, but it may also behave like something else. And that's the logic. So we started with that problem, which, by the way, was already raised by people like Feynman and de Wit. They were trying to make the statement that quantum theory or quantum system have a kind of totalitarian property, that when they interact with something else, they immediately infect it with this indefiniteness that is typical of quantum theory. And their arguments were based on some dynamical considerations, whereas the types of arguments that we proposed were based more on this principle-based type of approach that comes from constructor theory. There is a sense in which we feel that the prediction based on dynamical laws, although very powerful in a certain domain, are limited because, on the one hand, they are tied to this idea of fixed background, which could be time in classical physics or space-time in conventional classical general relativity, which is bound to break at some point if you imagine to quantize that background. And therefore, the idea of having a way of making predictions which uses, for example, principles about possible and impossible transformations seems to be promising, also because of the fact that it drops this idea of a prediction based on relative evolution with respect to some background.
It's not the first time that we are facing something like this in physics. So I think if you think 150 years ago, we had Newton's laws for particles and we had Maxwell's equations for waves. And the two actually described completely different sets of phenomena, and you couldn't unify them at all. And it actually led to quantum mechanics. But the way people came up with quantum mechanics was to distill the principles, the relevant ones, as they thought, out of both of these.
Right.
And for instance, energy conservation we knew was true in both of these theories, momentum conservation and things like that. And actually, when you applied this to the new situations, it still worked, and it ultimately led to quantum mechanics. This way of thinking that's based on principles rather than on coming up with a new dynamical law. Is very much how Einstein discovered, both special relativity, and then it led to general relativity. What's very hard to do as a scientist is to, first of all, to select what are the right principles, and then to see through all the logical consequences and come up with meaningful predictions that can be tested. So, Einstein started with these two principles saying nothing can travel faster than light, and all the laws of physics should be the same for all observers. And it looks intuitively appealing that this should be right, But what's amazing is to see the consequences of this. So what are the consequences? How would I test these consequences?
Which is what he did.
Which is exactly what he did. And actually the most striking consequence is that we don't perceive, different observers perceive space and time differently. So time ticks at a different rate for different observers. And that's by no means obvious, actually. It doesn't follow obviously from these two postulates, but actually it does. And I think with this kind of constructor theory principles, you want to do something very similar. You want to say, these principles sound very logical to me that they should hold. So for instance, if I combine a system that can process information in one way with another one that can process it differently, then the hybrid system should behave like this. But the question is, can we then see what this really implies for our measurements that are always done in space at a given time and so on? So I think ideally, you could maybe really turn it around the way Einstein did and even derive dynamical laws from some of these principles. That would be kind of the holy grail of the whole enterprise.
Okay.
So there is a phenomenon which is called a redshift, which is actually a prediction of general relativity, which predicts that photons in a gravitational field must change their frequency, their energy, under certain conditions. And this is a prediction of dynamical laws, really. But Bondi managed to make that same prediction by assuming two very simple principles. One is the conservation of energy, and the other one is the fact that energy and mass are equivalent. And he showed that if you don't have this redshift phenomenon, then you would break the conservation of energy because you would be able to build a perpetual motion machine made of atoms emitting photons. And this is a very nice example of what we would like to do with these new principles. Way of making a qualitative prediction about a phenomenon like redshift without actually knowing a particular dynamical law. Yes, another example of this cross-discipline problems is one that is the problem of understanding whether if you take a system which has been traditionally regarded as classical, which is a heat engine, and you consider what would happen if you were to replace some of its bits with objects that obey quantum theory in the sense that they support quantum effects, whether this might lead to a behavior which is different from the one predicted by current formulations of the laws of thermodynamics, and whether you could perhaps formulate a new scale-independent type of laws which generalize the laws of thermodynamics to cover such systems. And I think this is an enterprise that is currently going under the name of quantum thermodynamics, which again shows you how you have to bring together two disciplines, thermodynamics on the one hand and quantum theory on the other, which are traditionally regarded as applicable, one to the micro domain and the other one to the macro domain. You have to bring them together and try to make a new field out of both of them.
Yes, I think it's exciting because thermodynamics comes from macroscopic objects, and asking questions like what's the ultimate efficiency of a steam engine and things like that. So it powered the Industrial Revolution. But actually, now we are going into the micro domain. We are making these engines quantum mechanical, and the question arises whether these quantum steam engines and quantum refrigerators could actually be more efficient than the ones that are based on the laws of classical physics. So the question is very fundamental because you're again questioning the laws of thermodynamics in the quantum domain, but it could also lead to useful technologies where you improve on the existing efficiencies.
But it's also a really cool idea.
It's a cool question.
Because it's a question of, you define heat when you have large ensembles of particles, like a gas, an ideal gas or a non-ideal gas, whatever. And then the question is, could you actually define heat for a single quantum object? Is there a way, for example, of connecting heat to information theoretic concepts, which is a problem that had been investigated already pioneered by people like Landauer and then Charlie Bennett, but hasn't been quite cracked yet. And it's interesting that now there is this effort to address this problem, and that it might have some technological impact, as you were saying. But it's also foundational because it's bizarre that you can define something at a larger scale, and then you go to a smaller scale, this concept kind of seems to fade away. It would be interesting to see whether you can generalize it.
Yes, even here you have this interesting dichotomy that there is a school of thought that says we must use dynamical laws, open systems approach and so on, and that's how they're thinking quantum thermodynamics. And then you have this principle-driven logic as well. So both of these camps exist actually in the field. Which is interesting. I think that's exactly the region that's most interesting to test, is the one where they disagree.
Right.
Because you want to somehow decide which theory would win, or maybe it would be neither, maybe it would have to be a higher level theory that becomes either of the two in the special case, actually. And I think that's exactly what this experiment would test.
Yes, I guess there are in a way two camps. So some physicists would expect that in a situation where these two types of system interact with one another, the classical part prevails, and therefore there is no scope for such a thing as quantum gravity. Whereas the other camp would predict the opposite, that as soon as you have a qubit interacting with gravity must assume some quantum features too. And this proposed test is a way of discriminating between these two views.
And the third view, that perhaps both fail.
Yes, it's possible that both theories fail as well.
Yes.
Okay. So just to tease that out, what would the universe be like if quantum mechanics trumped general relativity? What would a quantum space-time be like?
Well, I guess this is the open question. So we actually don't have answers to that yet.
We have some predictions.
Yes.
We certainly have no experimental evidence, which is why I think we were proposing this kind of test. But some of the consequences of quantum gravity, if you really quantize gravity the same way you quantize all other fields, all other forces, would be, for instance, the existence of gravitons. So there should be, particles that mediate the gravitational interaction, the same way that photons are particles of light and mediate the electromagnetic interaction. That would be one prediction. But gravitons are tiny, and we already know that they would be exceedingly hard to detect directly, which is another reason why we were proposing a different kind of experiment.
Right. But I guess I'm really trying to ask you whether wider space-time, normally considered in general relativistic terms, would start to we would believe that it displayed the kind of spooky properties of quantum mechanics, like superposition.
Yes.
Like could large-scale bodies exist in two places at once, that kind of thing?
Yes.
If quantum mechanics trumped general relativity.
Yes, absolutely. If you put a large object in a superposition of two different places, if gravity is really quantum, then this would generate two different gravitational fields, which would exist simultaneously, one originating from the object being here and the other one from the object being there.
Right.
That sounds very confusing to a classical general relativist. This actually makes no sense. It's very hard to make sense of that classically.
Right. But
and one thing that also breaks down is this idea of having the idea of performing predictions with respect to a definite space-time, precisely because of the fact that it would have quantum features. So this indefiniteness that quantum theory has would spread to space-time in a way, and this would make it problematic to perform predictions in the standard sense.
Okay, so that's what would happen if quantum mechanics trumps general relativity. What about vice versa? I gathered people like Roger Penrose, for instance, say that it's the large-scale features of gravity and space-time that collapse the wave function in quantum mechanical experiments.
Yeah.
Is that correct? And is that all that would mean?
Yes, I think so. Again, the experiment we propose would be a test of that as well.
Okay.
Because I think in theories like Penrose's, a large enough object in a superposition would be forced by gravity to really exist in one of these locations or the other one, but never simultaneously. So there is a mass, a well-defined mass beyond which people like Roger Penrose would say you cannot superpose that anymore.
Okay.
Quantum physics fails. And in fact, what's interesting to us is that there are many other views predicting failure of quantum mechanics. Gravity is just one possible culprit. People say all sorts of things. If you look at it historically, people say, for instance, that living systems should also have this effect on quantum physics. So when a living system observes something, then it will never see a superposition of things. It will really impose a definitive location.
Yes, as if there were something special about this type of observers.
Exactly. So some people think there's something special about living systems as observers. I don't...
Because they're alive or just because they're a certain size?
Good question, actually. Yeah. None of these are clear, whether it's just a complexity or being alive, or do you have to be conscious even, Does it require a certain biological complexity to do that, to collapse the wave function? And I think experiments like this are exciting because they could also go into the biological domain.
Okay.
Rather than just superposing non-living systems and larger masses, maybe we could take viruses, bacteria, and go down that route and really see whether quantum physics collapses at any point.
Right.
Yes, perhaps I can say that one thing that was proposed as a criticism of this view that used to say that quantum theory fails at some point, which I think, as far as I know, it was the first voiced by Feynman, at least officially in this conference, which was called the Chapel Hill Conference, is that it would be desirable that if this were the case, a principle, a law could be formulated about what exactly it is that makes quantum theory fail. And there have been proposals to this effect, but to this day we don't have such a law. So perhaps one consequence of one breakthrough, if it were indeed the case that the quantum theory fails at some point, would be exactly to formulate this principle. And as far as we know, we don't have such a principle yet. And quantum theory, as it is, in principle, should apply to any type of object.
Yeah, so we're in a very much uncharted territory. We have to make guessworks, basically. What do we think is going to happen in an experiment like this? And again, you're kind of extrapolating from either GR or quantum physics. And you say, roughly, when I have these energies and masses, maybe something interesting happens. But we actually have no laws, really, to tell us exactly what would happen.
So one of the novel features of this experiment is that you would be using molecules large enough to exert gravitational forces on each other, and that's not been done before. Is that right?
Yes, exactly.
That's right. It's a very challenging experiment. So I think the general idea, the beautiful part is that you can actually show that whatever mediator is capable of inducing entanglement has to be quantum itself. In this case, this would be gravity. But if it happens to be anything else, let's say a living system mediating this, you could also then say it's got to have some quantum features. So our logic is universal and applies to any hybrid system. It's really nice. The downside of the experiment is that it's extremely hard to do because the masses that we require, simply because gravity is the weakest force that we have. So we need a mass large enough to have a certain effect in this experiment. So the masses that we're talking about are orders and orders of magnitude larger than what people are capable of at present. So, for instance, a million or even billion times heavier than the molecules that people are putting into superpositions currently.
Okay.
So there are some ideas that this could even be very challenging for an experiment on Earth. But people are planning all sorts of experiments on satellites where I think you could eliminate all sorts of noises much better.
Right.
And I think an experiment of this kind would be then feasible.
Because if you're trying to detect gravitational influences in very small bodies, which will be weak,
yes,
the further you are away from this great gravitational influence that we're standing on. Okay,
yes.
right, got it.
Yes. So we're talking about masses. Just to give you a rough idea, the masses, the mass that emerges naturally when you're trying to put together quantum and gravity is the Planck mass. And that's something like 10 to minus 8 kilograms. It's roughly how massive a human cell is, biological cell. Now that would be very hard to put in a superposition. Our masses are something like a million times lighter than that. So there is still hope that you could do this maybe even on Earth, but it becomes more and more challenging as you approach this Planck's mass.
Okay.
And I think the masses that we have in mind are certainly the ones where theories like Penrose's would say that this cannot be done either. They should not be really in a superposition.
So it's a really exciting proposition, which would cast light on so many things at once, right? So there's this question about whether the many worlds interpretation of quantum mechanics is correct, and if you prove that quantum mechanics trumps general relativity, then the world could exist in superpositions as well as just small quantum systems. You've also got this business of entangling things as large as a biological cell, potentially, and understanding the relationship between quantum mechanics and life. And it also really pushes in the direction of uniting quantum mechanics and general relativity, which I think most people understand is the holy grail of physics. And when are you going to do this?
We have to convince the experimentalists to undertake this enterprise.
Right. But you're hopeful it will happen in the next 5-10 years?
I think the challenge again is really to do, first of all, a detailed calculation.
Yes. Because I was going to say, yes, there are also other forces that come into the way of this, because the two masses have to be quite close to one another, and at that scale there are other forces other than gravity that would come into play. Even if the two masses are not charged, there could be still some electromagnetic interactions that are going on. So that's another huge difficulty that one would have to study more carefully.
Yeah, so I think that's part of our program would be certainly to do a full feasibility study. Then, of course, I think the real challenge is having enough funding to maintain these kind of experiments over the next 5 to 10 years, because that's probably the period that you need to execute them. The costs are there simply because to eliminate all sorts of sources of noise, you really need to cool your systems down, because the higher the temperature, the more they vibrate, and all of these quantum effects then basically become washed out. So you want to reduce the temperature, and there is a technology that exists for this, but it's extremely expensive to maintain. So I think that's also part of the challenge.
Okay. But are we talking more or less expensive than a super collider? Is this?
No, certainly not on the high energy. These are still atomic physics experiments. So roughly on the order maybe $1 million a year to maintain this kind of cryogenics should be enough.
Okay.
Yes, and I think what I find exciting is that even though this is driven by these big fundamental questions that may require a long amount of time to really answer. What's interesting is that there's always a possibility for new technologies to come out of that. And not just quantum computers. Quantum computers could be another long-term applications, but in the near term, for instance, you could envisage very sensitive detectors of fields like the magnetic field or even the gravitational field. And it's very exciting as it happens that when you put a mass in a superposition, that becomes much more sensitive to gravity actually than just a simple classical mass. So along the way, as we develop these experiments to test, for instance, the quantum nature of gravity, you could think of it in reverse as a technology that will give you a very sensitive measurement of the gravitational field. And this could have a range of applications.
For instance?
For instance, people worry a lot about the existence of underground holes that every once in a while cause your roads to collapse, for instance. This happens a lot. You can watch it on YouTube, I think. It's very hard to anticipate with these conventional methods where these holes would be. But actually, if you put a quantum system in a superposition and place it directly above this one, then in principle it could be sensitive enough to detect whether there is a hole there, because there is a different gravitational effect already at that scale. And people are envisaging that this could be a big application really, and it could save a lot of money, because currently we're just drilling in random parts and trying to anticipate where these things could be.
Right. And of course, you never know in advance about what kind of technology might come out of theoretical advances.
Yes.
You know, I was talking to David yesterday that James Laderman always cites the example of the laser, right? Because that just dropped out of these guys who realised that their theory had this strange consequence, and they built the laser to test it. And had no idea that we'd be playing music with lasers or correcting people's eyesight with lasers or whatever. It was just open-ended curiosity that came first, and then the technology just flows as a result.
I think very similar criticism even of people like Faraday. I think the famous story is that he was demonstrating what we call the Faraday induction now. You know, when you change the electric or the magnetic field, you will induce the other one, if you like. And I think in one of these presentations at the Royal Institution, someone got up and said, "What good is this, you know? It looks like a fancy effect, but so what, you know?" And I think Faraday's reply, I mean, of course, we know now that so much technology is based on this, that the question is superfluous now, but it wasn't clear to them in the 1850s. And I think Faraday's reply was, "What good is a newborn baby?" And I think a laser is a very similar example. You know, there was a newborn baby in the 60s, but now, of course, most of our technology is laser-driven. And I think we're envisaging that quantum effects will become the same.